And you can also integrate, and this is where it gets good, right? So we've done substitutions, we've done multiplication, we've done derivative. It's where you do the integral that this starts to really get interesting. So let's start with the 1 over 1 plus x that we derived here, all right? Because I know that the integral of 1 over 1 plus x dx is equal to ln of 1 plus x plus c, right? So if I do the integral of 1 over 1 plus x, I'm going to have ln of 1 plus x. We'll talk about the c in a little bit. So then all I have to do is look at what happens term by term to the series that I'm integrating. So I'm integrating this one. So if I do the integral of 1, I get x. If I do the integral of negative x, I get minus x squared over 2. If I do the integral of x squared, I get plus x cubed over 3, and so on. And then my next one is minus x fourth over 4. All right, and then that has to be equal to ln of 1 plus x. So this is the first one where we can see I have an infinite series, and it's not giving me a rational function. It's not giving me some other polynomial. It's giving me a transcendental function. So this is where we're starting to be able to evaluate, you know, what we're headed for. Like, what would the ln of 2 be, and how would I calculate that? So now let's try to write an expression for this one. So I'm going to have the sum. And I chose to do 1 to infinity on this one, just because it makes it easier, because then I can put in a negative 1 to the n for the alternating, and then I can just see it lines up nicely if I do 1, 2, 3. So that way I don't have a lot of minus 1s. So I chose 1 to infinity. I chose that. You can choose this index variable. Some people choose it differently. In this case, I think it nicely corresponds with what we have over here. And so what I have is x to the n over n. Right, and all of these converge on the interval negative 1 to 1 so far, right? So ln of 1 plus x has to be equal to that. So what else can we do is let's do the integral of this one, because I know that the integral, I was going to say about the plus c here. So what about the plus c? So I also know that the ln of 0 plus 1 is equal to 0. So that means that when when x equals 0, the sum has to be 0 as well. So that means that the plus c that I could put right here, that c has to equal 0 because of this. The c equals 0. So I could put in 0 for the x here. I get ln of 1 is 0. All of these terms will be 0 except for the plus c, so the plus c also has to be 0. All right, so that's ln of 1 plus x. Now, what about the antiderivative of 1 over 1 plus x squared? So I have integral of 1, let's get that lined up a little, 1 over 1 plus x squared dx. That equals inverse tangent of x plus c. Now plus c is going to turn out to be 0 this time also, because the inverse tangent of 0 is 0. All right, so then I know that I can get inverse tangent of x by integrating this one. So I'm going to integrate it term by term. Sometimes we say term-wise. The integral of x, the integral of 1 is x. The integral of negative x squared is going to be minus x cubed over 3. And then I'm going to have plus x fifth over 5 and minus x seventh over 7. And both of these go to infinity. All right. And then, so now I just need to find a way to express that one. I chose to stick with the same thing that I did here, which was n equals 1 to infinity, and then I get, so anytime you have odd numbers, 1, 3, 5, 7, that's always going to be 2n minus 1. Or if we had started with n equals 0, it would be 2n plus 1. All right, so you can check that out to see that it works. X to the 2n minus 1 over 2n minus 1. So the 2n minus 1 down here, when n equals 1, I have 2 minus 1 is 1. N equals 2, I have 4 minus 1 is 3. N equals 3, I have 6 minus 1 is 5. And the same thing happens in the top. So now I know that this series converges to inverse tangent. All right, so now what we've done is taken just the one series addition formula that we know, which is for geometric series, and we've done a bunch of things and gotten new series that describe functions. So all of these on the right are functions, all of these on the left are series, and the series are equal to the functions. They're equal. They're not approximations as long as we take infinitely many terms. But we can use them as approximations if that's what we want. Now what we're going to look at next is the most interesting two series here. The most interesting two results are these ones. So we're going to have a quick, an in-depth look at those two next.